Hey guys, today we're going to be taking a look at this problem. It's called Find If a Path Exists. This is going to be a graph type of problem where we're focusing on graph traversal. So, you are given an undirected graph with n nodes labeled from 0 to n minus 1 and a list of edges. Write a function that determines whether there is a path between a given source node and a destination node. So we got a sample input, 6 edges of 0 to 1, 0 to 2, 3 to 4, 4 to 5. So this is a graph given in like a matrix form, like a 2D array form, where each one represents an edge of the graph basically. And you see that there is going to be no path from when n is equal to 6. The output is going to be false because the source node, when you're trying to get to 0 and going to 5, you can go from 0 to 1, 0 to 2, but nothing connects from like 2 to 3. So there's no, or 1 to 3 or 1 to 4. So there's no possible way from you to start at point 0 and get to point 5. So that's essentially what this problem is asking for. Now, how do we do something like this? Well, let's get started by making the function. And what we want to do is basically do some sort of traversal through the graph. So the easiest way to do this is what we could use a depth first search approach. So if you guys remember, a depth first search approach is continuously going into the deepest node in a given tree and trying to find it from there. That was for a tree. This is for a graph instead. So let's start making the function n edges source destination. So let's make our graph first. Graph is equal to make a graph easily, where we can use an adjacency list format. So one easy way to do this is we could do I for, so in an adjacency list, if you don't remember, it's in the dictionary format where you have a key and then the value pairs, where each key represents a node on the graph, and each value associated with that key is a neighbor of that key. So what we could do is we could say for I in range of n. And basically all this does is this creates the adjacency list, and all we need to do is to fill in the graph for u comma v in edges. We're going to do graph of u dot append v, graph of v dot append u. So this is making the adjacency list for all the separate nodes. So like for example, when 0, 1, 0, 2, I don't know why 0, 2 is like that, but like imagine it looks like this. 0, you see there's going to be I is the key of 0, and then it's going to have the neighbors of 1 and 2 in each input. And obviously this is going to create the adjacency list graph. And to do a traversal, what we want to typically do is we'd have a set of the visited. So we're going to make a set called visited, and this is going to represent all the nodes that we continuously travel, and we're going to need this in order to perform our depth first search. Now, the easiest way to make a depth first search is using recursion. There's an iterative method too, but for this problem we're just going to be using the recursive method. The iterative method is, instead of using this, you could use a stack, but let's go with this. So for the depth first search, we could have a node. So remember, each time we encounter a node, what we want to do is we want to recursively call depth first search on itself, right? But what are we going to say? If node is equal to destination. So once we perform the depth first search, when we're traversing through the graph, once we find the node, obviously if it's equal to the destination, we want to return true, because we do know that yes, there is indeed a link between the node that you're starting from on the source and going to the destination. When they're equal to each other, then you would return true. And we can also add it to the visited list, because it means that well, not even if it's true, but in general, what we want to do is we want to start out by adding the node that we append into the visited set, basically. So it either immediately returns true because we reached the destination, or we're going to be adding it to the visited set. Now, what we can do for neighbor in graph node. So basically, all this is doing is we created this adjacency list, and when we say graph of node, that is referring to the keys, each key in this dictionary, and we're going to be basically saying for each value in the value side, the value list of each key, basically we're looping through. And if that neighbor, so like for example 0 goes in 1 and 1 to 2, so we would go 1 and then we go 2. If the neighbor is not in the visited list, that means we need to do a breadth search. We need to go there. So how can we go into that list? We perform the depth first search function recursively. So the depth first search of that neighbor, and that's how we do it. So if we see it, and eventually it's going to return true. If we recursively keep on going, like for example 0 goes to 1, 1 goes to any possible adjacency neighbors in 1, in this case there's nothing, so it's going to return, it won't even get to this return statement because it'll never reach the destination, which is this first return statement here. But since it's not, it's going to return false. So we can put the return false out here for when we never get to the destination from the source. And yeah, that's basically it. So this is the simplest way to create an adjacency list and set up the depth first search operation to start from a source node and getting to the destination node. Finally, we can return DFS of source. And yeah, that should be it. Now, obviously, we can take a look by testing it. We could use this test that I created earlier. And if we say we're going to print out the valid path, and we're going to enter all of these n, edges, source, and destination. And if we did everything right, we should see that since there is no link between 0 and 5, this should output false. Oops, sorry, I forgot when I was doing that, I messed up the implementation, and there we go, we get false. So 0 doesn't have any root towards 5, so it results in false. Sorry for this little side on the bottom right being a little bit wonky, but so yeah, that's pretty much it. We can test it out with another type to see if everything is aligned. We can go, let's say we want to see a true statement, so how will we get to 5? We can connect, instead of this to being 0 to 2, we can connect it from 1 to 4. And since there's a 0 to 1, 1 to 4, 4 to 5, this should instead return true. Did I run it right? 0 to 1, 1 to 4. For some reason this part isn't working. Did I enter anything wrong in this thing? Because I believe all the logic should be right. If node is equal to destination. Yeah, that should be pretty much it. Everything is outside. If we could say 0 to 5, obviously that should return true. I mean, I'd assume so. Did I save it? I didn't say. Wait, no, I did save it. So we're gonna do a little bit of bug testing here. Created our graph properly and edges source destination for u comma v and edges where we're going through the edges. Oh, for some reason I said in visited, but we need to say not in visited. If it's not in the visited list, that means we need to perform a depth first search on it. So my apologies, everybody. So now if we run this code, it should return true because it goes from 0 to 5 and then it sees that there's the element that is not in the visitors list that it needs to check, and it adds that to the visited list and performs the depth first search operation to return true. So yeah, that's basically it. Hopefully you guys understood everything and understood the logic. Sorry for that hiccup there. But yeah, that's pretty much it. See you.